Well, wouldn't you know, we're on the last section that we're going to do of Chapter 2 already, so you know what that means. Coming up, we're going to have our exam, and our exam will be this coming Thursday, and it will cover Chapters 1 and Chapter 2. We're going to look at one-to-one functions and their inverses. One-to-one functions, the inverse of a function, and graphing the inverse of a function. The inverse of a function is a rule that acts on the output of the function and produces the input. So you're going backwards. So it undoes or reverses what the function has done. Now, not all functions have inverses, and those that do are called one-to-one. So let's look at one-to-one functions. So we're going to compare these two. Now notice over here, for every x value, I have a different y value. So again, I'm saying for every x value, I have a different y value. I have 4 and 10, 3 and 7, 2 and 4, 1 and 2. This would mean that I could go backwards, and every one of these y values over here has a different x value if I go the other way around. So if I am reversing it, I still have unique answers. If I end up putting my range in for my domain, I can go the other way. Now over here, what I notice right away is that if I put the value of 3 in, I will get the value of 4. And if I put the value of 2 in, I will get the value of 4. Now we've seen parabolas where we have the same y values at different x values. That would be an example of something that is not one-to-one. It is a function because it will pass the vertical line test for a function, but it's not a one-to-one function. So just a reminder, again, f never takes on the same value twice. Any two numbers in A have different images. So G does take on the same number as twice. So 2 and 3 both have the same image of 4. Now, when they say same image, they're talking about the range values. So a function with a domain of A is called one-to-one if no two elements have the same image. So that means that everything that you put in for your domain has a different range. And that would also mean that those domain values are not the same either. So you can go one way and the other way, and everything is unique both ways. There's a test called a horizontal line test for one-to-one functions. Notice this function here hits the graph twice, or this function here, a horizontal line hits the graph twice. So this is not a one-to-one function. However, if I were to test this to ask, is it just a function? When I do my vertical line test, I can say, well, yeah, it's a function. So it can be a function, but not one-to-one. I also mentioned the parabola. If I have a parabola, we'll just take a look at the parent function here. And I want to do a vertical line test. I can see, oh, this is a function, no problem. But as soon as I do my horizontal line test, when I get here, I hit the graph twice. So this is not a one-to-one function. Not a one-to-one function. Nope. So again, horizontal line tests will we'll look to see if it's a one-to-one function. But first, it has to pass the vertical line test in order to go to the horizontal line test. So you have to make sure it is a function first by using the vertical line test. Okay, so don't get tripped up by that. It has to be a function first. So that means you're going to use the vertical line test first. And then after it passes the vertical line test, then you will use the horizontal line test to see if it passes that. And if it passes both, then it is a one-to-one function. Okay, so let's look at the parent function of a cubic graph. We can see that, again, we know that if our domain values are not equal, and we put those into x cubed, my range values are not equal. So it is a one-to-one function. Now you might be tripped up a little bit when you look at this part right here and say, well, it looks like the same values if I draw a horizontal line. Well, if you zoom in on that graph, you'll see that none of those are the same. It's steadily increasing. It starts here, it goes up, and it continues to go up through these values just a little bit, and then it continues to get steeper. So this does, in fact, pass the horizontal line test, and not only does it pass the horizontal line test, it also passes the vertical line test. So since it passes the vertical line test, and sorry, those vertical lines aren't very vertical, since it passes the vertical line test and the horizontal line test, it is a one-to-one function. So again, this is an increasing function from beginning to end. So what we know is that if it increases from beginning to end, or if it decreases from beginning to end, that it'll be a one-to-one function. And that just takes some logic here to think about. So if I'm starting here at the bottom and I'm going up and I continue to always go up and I never go back down, even if I change my slope a little bit, okay, I never go back down, then it's going to be a one-to-one function. Same if I'm starting up at the top and I'm swinging down around here and I continue to go down, then it's going to be a one-to-one function. All right, let's look at inverse functions now. Now that we've covered one-to-one functions, we'll talk about inverse functions. An inverse function is when you just go backwards. So you're undoing one function. And if it is a one-to-one function, then it does in fact have an inverse. So what that means is the domain of the inverse function, this is the symbol right here for inverse. This is not an exponent, it is a symbol for inverse, okay? Not an exponent. So if the domain of the inverse function is the range of the regular function, and the range of the inverse function is the domain of the function that I started with. So if I give you these values here, and I ask you, find the inverses of 5, 7, and 10. So what I am doing here is I'm looking at these function values that I get when I just put it into the regular function, and I'm going to figure out what the inverses are. So what I simply do is I take the value that's in here, 5, and I go and I see, well, what did I originally put in to get 5? I put 1 in. So the inverse function would be 1. So now I want to take the value of this function and plug it in here, and I see that I have 3. And then I want to take the value 10 and see what I put in to get, or negative 10 and see what I put in to get it, and I have 8. And if you hear a dog in the background, my son just walked in with his dog. So that's just Prince. That's not me doing that. All right, so now I have the inverse function of 5 is 1, again because of this. The inverse function of 7 is 3. And that should say because f of 3 is 7. So mistake there, so let's fix that. And then we have the inverse function of negative 10 is 8 because f of 8 is negative 10. Okay, so you can take a look at using an arrow diagram to kind of see this effect. And again, reminder, do not mistake the f of negative 1 for an exponent. It is not an exponent, okay? So it does not mean put 1 over the value and put it on the bottom of a fraction. Okay, so by definition, the inverse undoes what it does. If we start with x, we apply f, and then apply the inverse function. We will arrive back at x, where we started. So here is the definition. Now these properties show that they are inverses of each other. If you can start with 1, y equals f of x, and then take the inverse of it and then get x back. So it's kind of a test that you can use to see if they are inverses. So let's take a look at how to find an inverse of a function. Let's find the inverse of f of x equals 3x minus 2. First, we're going to change it to be y equals 3x minus 2, and then we're going to solve for x. So I'll add 2 to both sides and then finally divide by 3. Now I'm going to go to the next slide and move this over to the next slide. X equals y plus 2 over 3. And now I interchange x and y. So instead of x equals, I put y equals. Instead of y plus 2, I put x plus 2. So you're just swapping the x and the y at this point. So once you get it equal to x, you swap the x and the y. So the inverse function is in fact x plus 2 over 3. Now rational functions are a little more work, so but we can handle them, no problem. So let's find the inverse function here, and remember I want to solve for x. So first I'm going to change it to a y equals. So now I have y equals 2x plus 3 over x plus 1. And I need to solve for x. So I'm going to multiply both sides by the denominator so that I can move it over on the other side. And now I'm going to distribute my y value. So now I have this, yx minus y equals 2x plus 3. So keep that in mind as we go to the next slide, because now I'm going to want to take a look at taking the 2x, because it has an x, and moving it over here. And then I'll take my negative y and move it over here. So there it is after I moved the x's on one side and brought the single y to the other. Why did I bring the single y to the other side? Because it doesn't have an x. So now I can factor out my x value. Right here, I factored out my x. And then I'm going to divide both sides by y minus 2. And here we go. So the very last step is I'm going to put x back in here and make this the inverse function of x. So you see the very last step, I'm going to go back and put in my x values and say this is the inverse of it would be this. Okay, so I swap them once, then I swap them again. Graphing the inverse function. Graphing the inverse function, if you think about what you're doing, you're taking your domain of A and you're getting your B values, then you're using the range that was B and you're getting A values. So one point on one graph is AB, then on the other graph is BA. What that causes is a symmetry about the origin, and what we call that is, it's a symmetry about the parent function y equals x. And it looks like this. So here's our parent function that we know very well, y equals x. And I'm going to take a point that was on the first function, and I'm going to swap x and y and make it a point on my inverse function. So something that looks like over here in figure 9 that comes up here and looks like this, then in fact will now look like this. Okay, so again, I don't know if it's showing, if it'll show that when I'm just going by it. So let me put it here. This is my f function and this is my inverse function. So I swap my x and y values and notice it has a symmetry around y equals x. So now let's sketch our f of x equals the square root of x minus 2. You should be looking at that and see the minus 2 on the inside and understand that that is a shift on the x-axis. And is it a shift to the left or is it a shift to the right? It's a shift to the right. Then we're going to use the sketch to graph the inverse function. And finally, we'll find the equation for that. So again, here's our parent function, our square root of x, and we see that I'm subtracting 2, so that tells me that I'm shifting it to the right 2 units. So here it is. So I have my original. I take my parent function and I shift it to the right. So I graph that. And then I'm going to put in my y equals x symmetry line right here. And I take every point that I have on this line, and instead of the x value being 2 here, this is 2, 0. So let's just write that down as a point right here. I have 2, 0. Now this point is going to be 0, 2. So I just switched my x and y values. And if I do that for every single point along this line, then I will get this line. Well, not a line, graph. So now if I solve for y equals the square root of x minus 2 for x, and again, I have to note that my domain value for this is that x has to be greater than or equal, or y has to be greater than or equal to 0, okay, in order for that to work. Okay, so now I am going to set it equal to y, which they just reversed it. Now, how would I get x by itself? Well, I could square both sides. And then after I square both sides, I could add 2 to both sides. And I get x equals y squared plus 2. Now I'm going to interchange my x and my y. And this will be my inverse function. So you can see this is like a parabola that was raised up 2.